Yeah, Johnny Hart. They can't go because of the government.
Are we good to go? Okay, great. All right, so welcome back, everyone. So as I mentioned in the first part, we are going to spend a little bit more time on smooth gradient descent and talk about this this idea of acceleration, right? So as we mentioned in the previous talk, for the gradient descent algorithm for smooth functions and also well-conditioned functions doesn't achieve the optimal convergence guarantee for those class of problems. There's a different class of algorithms which is related but also quite different, which is called accelerated methods that will give us the optimal convergence rate. And as some of you might know, this is actually one of the most fundamental results in convex optimization, that we can achieve this accelerated convergences. And the algorithms that have been designed in that setting are quite beautiful and quite impactful, both in theory and in practice. So they're pretty fundamental to the design of fast algorithms in both of those settings. And at the same time, they're also quite mysterious, or they're perceived to be mysterious. And there's been quite a few developments that led to different interpretations of the original accelerated gradient descent method and related methods. And that means that my job is quite difficult, because I have to make a choice in this large space of possibilities. So I chose a specific algorithm, actually two algorithms that I want to show you, and I just want to motivate how one might go about designing those algorithms from what we've seen so far. And let me sort of preface that with the caveat that this is my intuition and yours could vary, and I'm very happy to talk to anyone that might have a different perspective. I think it's quite valuable. So we're going to see two algorithms that achieve the accelerated rates. They're related, but at the same time different, as we'll talk about later. And if time permits, we'll also talk a little bit more about four pointers, many things that I could not tell you about in these two lectures, as well as maybe we'll have time for some analysis. So maybe we'll see the analysis of smooth gradient descent, hopefully. Okay, so with further ado, so let us dive in and try to derive accelerated methods. But before we do that, make sure the clicker works. So before we do that, let us briefly recap some of the main ideas that we saw in gradient descent. And what we saw in gradient descent, so once again, this is a smooth objective function. So we saw that we can use smoothness to get an upper bound, a global upper bound on the function, which comes from smoothness. So we have this simple quadratic function that is upper bounding the function everywhere. And because the function is also convex, we saw that means that we have these global lower bounds, which are given by the first order Taylor approximation. And the gradient descent algorithm relied very strongly on both of those two properties in order to achieve good convergence. Right? So smoothness gave us this nice quadratic upper bound that we could use as a proxy for the function, and convexity gave us a nice affine lower bound that we can use to gauge how far away the minimum function value can be. So how small can the minimum function value can be? All right. So you see, in order to do better than gradient descent, an important idea that has emerged in the study of accelerated methods is that we can actually construct better lower bounds to the objective function that are more informative than the basic lower bound that we get from convexity. And in this lecture, I want to give you some recipe for building such lower bounds and give some intuition how to use it to achieve acceleration and actually derive an algorithm along the way. All right. So this is the goal of the lecture. Let's build better lower bounds to our function and hope that we can leverage it to converge faster. All right. Okay. So before we do that, so let me also make another algorithm design choice that will take us a little bit further away from gradient descent, which is that let us allow ourselves a little bit more flexibility in the algorithm design by separating our goal of constructing a solution, which is an approximate solution, from our goal of learning about the function by constructing suitable lower bounds to the function. So in gradient descent, if you think about it, we did both of those things using our just one solution, which was x, right? So we have this iterates xt. They were our main solution, and there were also the points where we queried the gradient, and therefore we got these affine lower bounds from those gradients. But they need not be the same. So we can query the gradient at other points that are not our main solution. And this gives us a little bit more flexibility in the algorithm design. So let us do that. So let us use, just to be consistent with gradient descent, let us use the iterates xt to query the gradients. So those will be the points at which we're going to query the gradients. And those will be the points at which we're going to get lower bounds from convexity, right? So these affine lower bounds, just as before. But let us allow us to use a different sequence of iterates, let us call it zt, to construct our main solution. So with that in mind, let us go back to this task that we set out for ourselves, which is to get better lower bounds on the function. And in fact, here the observation is quite simple, which is that in gradient descent, we are only using the current lower bound that is given by the current iterate. But in fact, we've observed quite a few gradients along the way, right? So in iteration t, we've already observed t gradients, each of which is going to give us an affine lower bound to the function. And as is hopefully clear from this picture, even two of those lower bounds is actually better than just a single one, right? So we could potentially try to be less forgetful and not forget about all of this useful information that we got from the past gradients that is giving us a better lower bound on the function, right? So it's in other words, right? So if we look at each of these gradients that we've queried so far, each of them is giving us a lower bound, right? So here we have a lower bound from x1, but also a lower bound from x2. And those two lower bounds together, they give us more information than each of them alone. So for example, if we could look at the maximum of those, right? So it's much better than each of them alone. So we could use the maximum as a global lower bound. So that is fine. It is a lower bound. But it has one downside, which turns out to be quite significant, which is that this lower bound is going to get very complicated, right? So the more gradients we're going to get, the more piecewise linear this function is going to get. So it gets very complicated very quickly. It is very hard to work with such a lower bound, although in principle we could. It turns out that we can do something fair bit simpler, which is simply to maybe, let's say, average these lower bounds. Or more generally, just take some convex combination of these lower bounds. So for example, here, this dashed line is the average of those two lower bounds. So we're going to work with that, right? So the convex combination of these lower bounds maintains this nice structure of having an affine function, which is very easy to work with. So let us go with this simpler choice instead. It's not as powerful, but it's much less complicated. Right, so we settled that we're combining these lower bounds using some convex combination. And this is actually completely up to us how we do this choice. And actually, a priori, it's not at all clear how we should combine them. And so let us allow ourselves just to just have the flexibility to choose any weights to combine these lower bounds. And here, we're going to choose these weights to be at least one, right? So we have these weights AT, one for each lower bound and each iterate. And we're using them to combine all of the lower bounds that we got from convexity into a single affine lower bound, which is the convex combination of those. So one thing that is good for intuition, which might be good to keep in mind, is that we will use the weights that are actually increasing with t. And this is putting more emphasis on later iterates, which are hopefully better solutions. So the intuition is that as we're getting closer to as we're further along in the optimization process, so in later iterations, we should be getting closer to the optimum. And therefore, the later iterates are better solutions, and we should emphasize the information that we get from them more. And this is captured by us using weights that are increasing with t. But otherwise, we can think generically for now that we have these weights that we're using to combine the lower bounds. Good. Okay. Good. So we've got our lower bound, right? It is this convex combination, some suitable convex combination of all of the lower bounds we have so far. And we would like to use it somehow, right? So now that we have the lower bound, we need to think about how were we hoping to use it, and how did it come about, come into play into gradient descent. So if we think back at gradient descent, there was this optimization perspective that I offered at that time that I suggested it's a good way to think about gradient descent, even if it's unconstrained. And we already saw why that was beneficial just in gradient descent, but let us exploit it even further now in accelerated gradient descent. So what was that optimization perspective? So what he said is that if we can think of the next iterative gradient descent as being the optimizer of this objective, which is combining the lower bound that we get from convexity with a term which is the movement, that how much the point is moving from the current point, the current solution xt. Right? So that's the optimization perspective that we saw for gradient descent, where we minimizing this combination of the lower bound and the movement together. So if we take that perspective, now given that we have a better lower bound, hopefully better lower bound, and a more global lower bound on the function that is taking into account all of what we've seen so far, let us try to use it in a similar way. So let us take inspiration from gradient descent and essentially plug and play, right? So before we were using a simple lower bound just at the current iterate. Now we have a more sophisticated one that is taking all of the previous iterates. So let us use it just like that. So here, what we're doing is that in order to construct our main solution, which now is no longer x, right? So if you remember, we allowed ourselves to use a different solution than the sequence where we compute the gradients. That was zt. So our solution zt, let us compute it by considering this more sophisticated lower bound that we constructed, and minimize the lower bound plus some movement term, right? Just like gradient descent. So plug and play. But now we need to think about what should go in the movement part, right? So in gradient descent, right, we had the movement was simply the distance between the new point and xt, which was the current iterate, because we were looking locally at the linear approximation at the current point. Right? And we didn't really use any global structure. We also used just a affine lower bound at that particular point. But here we're taking a more global view where we're incorporating all of the previous lower bounds and all of the previous iterates. And it turns out because of that, it makes sense to actually use a different movement term, which is simply to look at the distance not from the previous iterate, which was zt minus 1, but rather the very first one. So we would just reference back to the initial point z0 and our movement is simply the distance to the initial point. Okay. So this might seem a little bit strange, but as we'll see a little bit more in a bit, this actually makes quite a bit of sense given the kind of lower bound that we're actually considering here. So that gives us one update strategy that we could use to update our main sequence, right? So it was just a more or less plug and play, taking inspiration from gradient descent, where we plugged in our hopefully much better lower bound, and we also add the movement to make sure we're not moving too far away, and we're combining those two and minimizing the combined objective.
Yeah, that makes sense too. We change Z0 to the average point, or that's not the right thing. So that like a reset as you go along, or like that is simply the 1 over T sum of the air. That's completely.
That's a great question. So Changa is asking, do other choices for the reference point, right? So here we're looking at the movement with respect to some reference points. So in gradient descent, the reference point was just the previous iterate. Here we're using the initial point as the reference point, and we're computing how much we move from that point. And Chana is asking, are there other natural strategies, like, for example, looking at the average of the iterates that will also work here? So the short answer is I'm not sure. For this particular type of lower bound, this is a very natural choice, and we'll see the intuition for that. But if we change the lower bound slightly, we may be able to use other reference points, but I'm off the top of my head, I will have to think about it. So maybe I can.
Or maybe phases in which you get a new starting point based on the previous phase or something like that. I mean,
yes. So what Phil is suggesting is that maybe you can also do it in phases where we break things up and we allow the initial point to change. So each phase will start with its own initial solution, which let's say is perhaps I'm guessing the last iterate from the previous phase. Can we do it that way as well? So I think it's sort of maybe the short answer is I would expect that all of this can be done, and one will could potentially get an algorithm like this, but I will definitely have to think about the specific details.
It seems that you are playing with two different ideas, right? Separating the axis with and the z's and these sophisticated all.
Correct.
So each one of them alone would not do.
As far as so yes, great. So that's a very good question. So there was an observation and a question. So the observation was that there are two ideas at play here. One is that we are decoupling the construction of the lower bounds from the construction of the main solution. And also, we're using better lower bounds, right? So those are the two ideas that we're using here. So that's correct. And the question was, would either just only one of those ideas alone suffice? So if we're simply decoupling I suppose so, yes, but I think we would need to think about it very carefully, right? So if we're just simply separating X and Z, we still need a good way to update X and update D. So that by itself, it doesn't allow us to go beyond just separating X and Z. So we would have to use some ideas, and these ideas that we're using here allow us to separate X and Z, and also come up with appropriate strategies for updating X and Z. For the second one, is it necessary to separate them? So in this viewpoint, yes, because our goal is actually to explore the function more. In that sense, of course, there could be other ways to do it, but here we want to explore the function more. So we want to be able to query gradients that are not necessarily our solutions, simply for the purpose of getting more information on the function from the lower bound perspective. So I may be exploring over here, so my solutions are here, or maybe even here, and they're pretty good. I have no reason to jump all the way here, but I may want to do that to learn more what's on the other side. I hope that makes sense. What's this? Question? Great questions. All right, good. So, so that gives us a strategy for updating Z. And also, just as we did for gradient descent, of course, we can drop the terms. So here we have like a complicated optimization problem, but several of those terms are constant that do not actually depend on the variable we're minimizing over. So we can drop those and simplify the update a bit, right? So we can just drop all of those constant terms. Okay. All right, so that gives us an update for the main iterates, right? So we're updating in this way, which was motivated by our choice of lower bounds and also the way the gradient descent algorithm works, at least from the optimization perspective that we saw. So let us follow the gradient descent a bit more in this regard, and also set these step sizes eta t, right, that we had there, right? So 1 over eta t was this coefficient that we used to weigh the movement term with respect to the lower bound term. So that's what we did in gradient descent. And the way we set eta t for smooth functions that leverage the smoothness was to say set eta t to 1 over the smoothness. So let us go ahead and follow gradient descent once more in that particular case as well and set eta t to be 1 over L. And that it specifies the step size, and we have a complete update for Z, provided that we have the gradients. So we haven't talked about just yet how to determine where we're going to query the gradient, but at least we know how to update Z once we have those gradients. Okay. So with that in mind, let us mention an important caveat, which is we can think of it as both a caveat but also a very important feature of this approach, which is that unlike the smooth gradient descent algorithm that we saw, right? So we saw the smooth gradient descent. We chose the step sizes to be 1 over L precisely so that we can make a step size that is as large as we could make it, while still making sure that the objective was monotonically non-increasing. So one might ask whether a similar property still holds in this setting, in this update that we have here, where we're actually using a different lower bound. And the answer is no. So now the objective function is no longer monotonically decreasing or non-increasing. It could sometimes go up and sometimes it goes down. And this is, in some sense, a price that we're paying for learning more about the function from the lower bound side. So we're willing to sacrifice this monotonicity process and this steady progress in the hopes that we're actually learning more about the function that will ultimately allow us to converge faster.
Alina, is it 80 missing or it is something?
Sorry?
1 over 80 missing in that? Or I mean, is it?
Yeah, so I dropped it because it is a constant. So I just simplified it. So 1 over 80 was completely outside. Mm-hmm. Yeah. Oh, sorry. The question was whether we're missing 1 over capital AT from the update, and yeah. So in the simplified update, we dropped all of the constant terms, including this 1/T factor that we had right at the front, which was multiplying everything in this particular choice of update.
Like outside the eta t thing, like this is weighing linear combination of lower bounds, right? But the 1/2 eta thing is separate, right? So
Yes, so I put it inside. Yes.
The regularization is sort of getting weaker.
Yes. Thank you. That's a great point. Okay. All right, great. All right. It is increasing over time. Mm-hmm. Good. So this is just to maybe sort of make a small comment before we go on. So as was already pointed out, these are specific choices that we're making here, and there are many other ideas that one could try to play with, and that's actually, I think, a great idea to get some understanding of the accelerator methods, to consider all of the different ways we could try to go about deriving an update scheme. So for the students in the audience who are interested in this, I think this is a wonderful exercise. All right, great, good. So as I mentioned, there's this caveat that the function value is no longer monotonically decreasing. And that's both the caveat, but it's also by design. This actually turns out to be very important for acceleration. But this brings about the question of whether we should still use the last iterate as our final solution. And because the function value is no longer monotonically decreasing, it actually makes sense to use the non-smooth gradient descent idea of averaging the iterates. And that's what we can use here as well. So we can have our actual solution that we're going to return to be the average of these ZT iterates. But now, because we have this much more sophisticated lower bound that is emphasizing different iterates differently, it makes sense to have a weighted average of the iterates that incorporates those weights. So we take a weighted average of the ZIs with the weights given by AI as well. And just as before, we're using weights that are changing with T, and in fact, they're increasing with T to put more emphasis on later iterations. Good. All right. So that tells us how we update Z, and it also tells us how we're going to construct the final solution. So the only thing that remains for us to understand is where should we query our gradients?
Sorry, one more question about that. Is f of z bar t monotonically decreasing?
Yes. I think so. Of course. Well, so we are going to return the capital Z, so Z bar T, which is capital T, the last iterate. So the average of all of the iterates. Right? So that is our final solution. All right. So at which point should we create a gradient? Right. So that's a very important question, right? Because the points at which we create the gradient give us the lower bounds that we are going to use to construct our main solution. So if we think about it, and actually if we sort of work through a little bit of the analysis of gradient descent, and as some of us have done in the past, you realize that there's this very interesting thing that happens. So sometimes we can make a very simple mistake in the analysis of gradient descent that gives us a guarantee that is too good to be true. And that happens when we accidentally use the gradient at the current solution, the new iterate that we actually don't have. So if you want to try it, you can see that is actually a very good way to get a very fast conversion that unfortunately is not correct. And sort of, so what happens there is that actually, if we could somehow query the gradient at the current solution, that would actually be great. But of course, we cannot do that, right? So I cannot query it at iteration t, right? I need the first t gradients in order to compute zt. So we don't actually have zt. We only have the first t minus 1. So we cannot query at z bar t. So that is, of course, a very fundamental difficulty there. But here's a nice idea. How about we just proceed optimistically, right? So in gradient descent, intuitively, we should not be moving too much from the current iterate, right? It is still an iterative, somewhat local method, right? So intuitively, zt should not be too different from zt minus 1, right? the previous iterate. So how about we proceed optimistically and we assume that this is actually the case, that they're actually pretty close. So in other words, let us use zt minus 1 in lieu of zt, right? So before, right, we had the convex combination of the first t iterates, and now we only have the first t minus 1 of them. So let's just add zt minus 1 in, where zt was. So that's one approach we can take for xt. So if we put all of those things together, we're going to get an actual algorithm, right? So now we've specified almost everything except the choices of weights. So let us put everything together, right? So we've arrived at an algorithm that looks something like this. So we start with some initial point, z0, and we pick some weights, right, at. And we perform this update for t iterations, right? So we query the gradient at this point xt, which is using some combination of the iterates from the previous iterations in an optimistic way, thinking ahead of the actual solution, which is a weighted average of the z's. And we update z using this combined lower bound that we had, plus this movement with respect to the initial point. And at the end, we return the weighted average of all of the ZTs. So that is the algorithm. So this algorithm was discovered in a couple of papers, and it goes by a couple of different names. Yes, one of them is AGD plus in connection to AGD, which is the accelerated gradient descent method of Nesterov. So that's the algorithm. So modular the weights, this is a complete algorithm. So let me.
What does the plus stand for?
It's the usual. So the question is, what does the plus stand for?
What's the difference to the?
So the question is, what is the difference between this method and the original, one of the original Nesterov accelerated gradient descent methods? So maybe we can take that question offline. It takes a bit of time to explain, but I'm happy to go into the details if you're interested.
So if you define xt to be z bar t minus 1, that's not good enough?
I don't know how to analyze it, I think. I will have to think about that. So yes, oh, sorry, I keep forgetting to repeat the question. So the question was, so here we said, right, that we were going to drop in ZT minus 1 for ZD, right? And try to mimic the way the actual weighted average is constructed. So what if we didn't do that? And just take z bar t minus 1. So I think that there's a fairly good technical reason why That might not be a good idea, but maybe that is a discussion we can take offline. Since I don't have a concise explanation as to what is happening, that goes wrong. All right, good. Good. So that is an algorithm. But how about these weights, right? So how should we choose these weights? So we said that they should be increasing with t to put more emphasis on the later iterations. But what is a good choice for it? So it turns out that a good choice for it is to just set them to basically t. So it's t times so actually 1 plus t over 3 is, for example, one choice that will work. So then on the order little t, which means that right as the iteration counter is increasing, the weight is increasing as roughly t, and this will give us the optimal convergence that we mentioned before. So the convergence to get an epsilon approximate solution now improves from 1 over epsilon, which was the smooth gradient descent guarantee, to square root of 1 over epsilon, which is significantly better. And this is the optimal convergence guarantee in this black box model. So this is one algorithm. So one thing we can do just to get a little bit more intuition is actually to think about what happens back in the unconstrained setting, right? So here, so this algorithm works even in the constrained setting, right? So we're optimizing over the feasible domain. But let us see what happens if the domain was actually unconstrained. So if k was all of r to the d. So then, right, this optimization problem is very easy to solve, right? So just take the gradient and set it to 0 and see what happens, right? So if we do that, we're going to see that zt is the initial point z0 minus 1 over L times the sum of these linear combinations of the gradients, right, with weights ai, right? And so that's the completely unrolling zt all the way to z0. But of course, we could look at it a little bit more locally and observe that this is also the previous iterate, zt minus 1, minus the current gradient, right? 1 over L times at times the current gradient. So we can also think of it a little bit more locally as zt minus 1 minus some factor times the current gradient. And if we want to turn it back into an optimization problem, just like we did for gradient descent, this gives us this update here, right? Where we have at times the inner product between the current gradient and y, which is what we're minimizing over, plus L over 2, just like in gradient descent, times the distance squared from the previous iterate. Right? So here, right, in this rewriting of the update, at least in the unconstrained setting, we go back to actually measuring the movement with respect to the previous iterate as opposed to the initial one. And this is also provides some intuition as to why the initial iterate was a good choice for the movement in this form of the update where we actually use all of the previous gradients. Okay. So in the unconstrained setting, this is an alternative way to write the update, which is at least semantically closer to gradient descent, right? So we have the inner product with the current gradient plus the movement with respect to the previous iterate. And the crucial point is that now we're actually weighing the inner product by a suitable way that is actually increasing with t. And this is the unconstrained version of a different algorithm, which was proposed by Lan. It's called ACSA. And it was proposed for a different motivation in the stochastic setting, and we're going to talk a little bit about this in a bit. And ACSA in the constraint setting is simply this update, right, where we actually use a constraint domain. So So in the unconstrained setting, the two algorithms are exactly the same, but in the constrained setting, they're actually different. So one is using this, can think of it, unenrolled. It was also called like a dual averaging style of update, whereas the other is using more of a gradient descent style approach. Okay. And as I mentioned, these two algorithms are two of several accelerator methods that have been developed along the way. And they're also different from accelerated gradient descent, so Nesterov's original method. And I'm happy to talk about the differences offline. And one motivation for deriving these alternate methods was the fact that sometimes acceleration doesn't play very well with stochastic gradients. So in the deterministic setting where we have exact gradients, all of these different accelerator methods, theoretically, they all give us the optimal convergence. They converge at the optimal rate and behave very nice theoretically. But if we go to other settings, such as stochastic gradients, we actually start to observe some differences between these different methods. And this appears both in theory and in practice. Some methods might not converge at all, even in theory or in practice, or they might converge at a different rate. And if you're interested in this topic, Maurice Hart had a very interesting blog post from a few years ago where he actually looked into this specifically for Nesterov's accelerated gradient descent method. And you can have a look. All right. Okay, so let me make a summary and also give you some 4 pointers of everything we've seen so far. And if time permits, we can talk a little bit about analysis of gradient descent. Just to summarize, so what we've seen today was a gradient descent template, and also for both in the unaccelerated setting and the accelerated setting. And combined, it gives us a powerful framework for designing fast algorithms for fundamental problems, both in the discrete optimizations, such as maximum flows and many other problems, as well as continuous optimization problems in many domains. And this is a very fascinating and very broad area. And there are many topics we did not get to cover, which are very helpful. And I'll briefly mention some of these here in case people are interested in learning more about them. So one thing we did throughout was that we stayed in this simple setting where we were measuring distances using Euclidean distances. So everything was we were measuring distances in the Euclidean norm, and we were designing the algorithms accordingly. But it turns out that the Euclidean norm is not necessarily the best way to measure how 2 points, how similar are 2 points in certain settings. So for example, if we think about probability distributions, so if the domain is the probability simplex, it turns out that there are better ways to measure the distances between 2 probability distributions. And some of you who have seen information theory might have come across notions such as the Kale divergence that is very good for that setting. And there's this very broad and powerful framework called mirror descent that allows us to incorporate distances that are not necessarily Euclidean and derive very good algorithms with very good performance. There's also frameworks for designing offline algorithms, like the iterative algorithms, like the ones we've seen in this talk, that are actually derived from online optimization. So many of us are familiar with the multiplicative weights update method, which comes from the learning from expert advice setting. And there are also other ideas such as the follow the leader algorithms, and also things like optimistic gradient descent, and many other ideas that were designed in the online optimization setting, which have very useful applications even for offline optimization. And another topic we didn't talk about was how should we do constraint optimization where efficient projections are not available. In certain combinatorial optimization problems, quadratic optimization and projections are very expensive, but other optimizations such as linear optimization is more efficient. So one can think about, for example, the greedy algorithm for matroids and some modular polytopes, there we can do linear optimization much faster. And there's a question of whether we can leverage that instead of projections. And there are methods that are designed to do that, such as the Frank-Bolt algorithm and many others. Okay. So another topic that we haven't talked about it yet, I hope to give you one analysis, but for unaccelerated smooth gradient descent. But it is a very fascinating and very revealing topic, is to understand how to analyze the convergence of all of these gradient descent methods. And to that, there are many wonderful references, and I quite like this survey by Nikhil and Anupam, which was very revealing to me when I started studying this topic. All right. So with that in mind, I think we have a few minutes left. Is that right? Okay. We have a few minutes left. So let me at least try to give you a glimpse of how one might design an analysis of gradient descent methods. And I'll pick something that is relatively simple so that we can go over it in a few minutes. So let us go back to smooth gradient descent. So without acceleration, so we saw this algorithm in the first part of this lecture. So it was this very nice algorithm that I used the quadratic upper bound coming from smoothness and minimized that. And that gave us the gradient descent, with step size is 1/L. So let us show that it converges as this 1/T rate that I mentioned in the first part, or in other words, at this 1/epsilon rate, where epsilon is the approximation that we're shooting for. Okay. And along the way, I hope to sort of give you a glimpse of how one might go about reasoning about these iterative methods and some of the ideas that go behind the analysis. And hopefully you can use that to analyze some of the other settings that we've considered. Okay, so with that, let us go ahead and do that. So the first idea that we're going to use for the analysis is to actually leverage smoothness. So if you remember, smoothness was this property that the gradient doesn't change very fast. So if we don't move too much, the gradient doesn't change by too much. So that means that intuitively, the next iterate, which is xt plus 1, should be intuitively close to the current iterate xt, right? By the way we designed the optimization method, right? So we incorporate the movement from xt as part of our objectives to enforce the algorithm, to encourage the algorithm to stay close to xt. So we can use this idea to try to analyze the function value gap. Right, so we have this new solution xt plus 1, and we are trying to understand how far away is from the optimum. And the way we can do that is to first just break it up and see how much we're improving, right? So how much better is f of xt plus 1 compared to f of xt, right? So that is the first part, plus the function value gap of xt, f of xt minus f of x star. And using our intuition that xt plus 1 and xt should be fairly close to each other, it seems reasonable to use smoothness to upper bound this difference. And for this part, right, so the function value gap to x star, so there we need to leverage a convexity, right? Because the only way we know how to gauge how large f of x star is via our affine lower bounds given by the gradient. So we can use that to upper bound to that term as well. Okay, so let's go ahead and do that. So we apply smoothness for the first difference, and we apply convexity for the second difference. And this is what we get, right? So this from smoothness, we get this inner product plus this distance squared term. So this is the movement squared between the new iterate and the old one. And by convexity, just by rearranging that inequality that we saw, this difference is at most the inner product with xt minus x star. So we get this upper bound where we have this inner product between the gradient at xt and xt plus 1 minus x star, plus L over 2 times the xt plus 1 minus xt squared. So now we need to understand this inner product, right? So we need to understand how large can this inner product be. So if we look at the inner product between the gradient and the direction between the new iterate and x star, what can we say about that? Okay. And here, the way I like to think about this is actually to think about what xt plus 1 is. And once again, this is where the optimization perspective comes in very handy. So the way we define xt plus 1 was to be the minimizer of this optimization problem, where we took the affine approximation in this movement term, and we minimized that to get xt plus 1. So that means that we can gauge what is happening with xt plus 1 by thinking back to our good old optimality condition, right, that we learned in calculus. So if the problem is unconstrained, the optimality condition says that if I take the derivative or the gradient and set it to 0, then I'll get the optimum. In the constraint setting, there's a version of this that looks a little bit different, but it's also very natural. So what it says is that if I'm looking at the minimizer of some function, let's call it phi, then at this minimizer, I have this nice property that the gradient of the function at the minimizer times the direction between the minimizer and any point in the feasible domain, this inner product should be at most 0. And the reason is that this direction, y star minus y, should not be a descent direction. I should not be able to improve the objective value by moving in that direction, because y star is the minimizer, and therefore I should. So this is not a descent direction. So that inner product is at most 0. Okay. So if we apply it, what happens, right? So xt plus 1 is the minimizer of this function that we put there in our update rule. So if it's a simple quadratic, so let's take its derivative. So we get the gradient at xt plus L times y minus xt. And if we apply the optimality condition, then we get this property that this inner product is at most 0. So this is a little bit fast, but really all we're doing here is very simple. We're just applying the first order optimality condition absolutely mechanically and seeing what happens. All right. So that's what we do, and we get this guarantee on this inner product that just falls out of the optimality condition. And this is a guarantee that holds for any point in the feasible domain by the optimality condition. But of course, for us, it's most useful when that point happens to be the minimum x star that we are trying to converge to, right? So we can go ahead and apply it with x star as the point of reference, and we can rearrange it. And now we can see that it is going to give us an upper bound on the inner product that we obtained before, right? So when we looked at how the function gap was evolving, this was the inner product that we're interested in. And the really nice thing about this is that we get a very nice upper bound on it straight by the optimality condition. So this is a very useful way to gauge that inner product. Okay. But of course, what we have here is not exactly that easy to work with, right? So we have some other inner product, and it looks a bit mysterious. So what do we do with this? And actually here, there's actually a slight algebraic trick that I like. It's not the only way to think about this, but I really like this. So whenever I look at an inner product like this, it's very useful to observe that. Did I move it right? And I think I have a typo there. Should be x star minus xt plus 1. So the point is that we have this very nice simple structure here. So where we're having some vector times some other vector, and these terms are shared. And whenever I see that, I think about this very useful identity, which is that the way I can write A times B is first to take the sum and square it, so 1/2 times the sum squared, and then subtract the terms that should not be there, right? So 1/2 a squared minus 1/2 b squared, right? So let me fix that typo real quick. Right. So yeah, sorry about that. So all we did here was to just move this term to the other side, right? So we got xt minus xt plus 1 times xt plus 1 minus x star. So on the other side, we have this very nice inner product that has this really nice structure, which is amenable to this identity, right? That if we can think of a times b as 1/2 a plus b squared minus 1/2 a squared minus 1/2 b squared. And if we applied it to this, right, we get a very nice equivalent way of writing this inner product, which is simply xt plus 1 minus x squared star squared minus xt minus x star squared. So this is very nice because it's a telescoping sum. And we also get this term, which is subtracting the distance squared between the new iterate and the old one, right, via that nice identity. And if we put those two things together, we get a very nice upper bound of the function value gap, right? So just to recap, so we applied smoothness and convexity to upper bound the function value gap, and that gave us this inner product that we needed to understand. And then we use the optimality condition and see what happens, and that also gave us a very nice upper bound on the inner product. So we can combine the two and get a very nice upper bound on the function value gap, which is simply this telescoping terms, right? So we have the distance between x star and the new iterate xt plus 1 minus the distance between xt and x star squared. And this is very nice because it telescopes when we sum everything up. So if we sum everything up and telescope, we can upper bound the sum by just the initial distance times the smoothness. And as we saw before, the function values are decreasing or non-increasing. So we can get an upper bound of the function value gap of the final iterate as the average of, right? So 1/t times the sum that we had there, and that exactly gives us the convergence that we were looking for. So that might have been a little bit fast, and it's by no means the only way to do this analysis. Actually, there are many fascinating ways to do the analysis, and Anupam surveys a great tool and resource for that as well. But hopefully give you a glimpse of how we might go about leveraging some of the ideas that are built into gradient descent, things like the lower bounds that come from convexity and this optimization perspective. And with that in mind, let me thank you for your attention, and I'm happy to answer questions.
Thank you. Questions?
So would the analysis for a case where we just have a subgradient be the same?
Many of the ideas, yes. So another reason why I like this template is because I can use a lot of the ideas. So the very first step is not going to be the same. So at the very beginning, we started by leveraging, sorry, let me go back. we started by leveraging smoothness by decomposing things in this way. So of course we cannot do that if the function is non-smooth. So instead, what we can do is actually start off by the second step, where we actually look at the optimality condition. So we can bypass this and go straight to the second idea and use the optimality condition. And of course that works no matter what, right? So we're still going to get this. Of course, this is with the step size in here. That is not one row. And we can write things nicely and so forth. So we can do this algebraic approach that I mentioned just as well. So all of this is great. The only problem with it now is that this inner product is not exactly what we want to understand if the function is non-smooth. And the reason is simply because if the function is non-smooth, all we have going for us is convexity. And what we get from convexity, well, from convexity, what I'm getting is that my function value gap, right, is upper bounded by the inner product with the gradient times xt minus x star, right? So if you remember, right, so we have, so this is xt, and we have this lower bound, and the gap is the inner product. And the crucial thing is that here is xt, not xt plus 1. So the optimality condition only allows me to reason about this inner product with xt plus 1, the new iterate, right? So this is the key distinction. So actually, what I really want to understand in the non-smooth setting is this inner product. But what I can understand via the optimality condition is this other inner product where xt is replaced by xt plus 1. So we need to do one more step to fix it. So we need to do one more step to fix it, which is, and the approach is actually quite simple, and that's where the Lipschitz property, the bounded gradient, is going to come in. And we're just going to break this up, right? So we are going to break it up into xt minus x star plus what is left, right? Xt plus 1 minus xt, right? Or rather, the other way around. So that's how we can gauge things. And then we're going to have this term. But the really cool thing is that we can actually get rid of that term if the gradients are bounded, because we actually have a gain. So here, from the optimality condition, we have this gain, which is the distance squared between xt plus 1 and xt. And that will exactly allow us to offset this loss here, which is the gradient times xt plus 1 minus xt, because the gradients are bounded. So if this distance is blowing up, it was only blowing up with the length of xt plus 1. Whereas what I gain here is actually the square of the length, which is going to overpower it. So that's at a high level how you do. But if you do all of this, it's going to give you an analysis.
Thank you.
I just wanted to ask if the AGD plus also works when like the same. Can you prove it's optimal under the mu strongly convex, like the one you showed before in the previous lecture?
Yes, great question. So yeah, sorry. That's a great question. So when we did gradient descent, when we had strong convexity, we didn't have to change the algorithm. The algorithm was still the smooth gradient descent algorithm. We just got the faster acceleration, the log 1 over epsilon convergence for free without changing the algorithm. In the accelerated setting, we need to know the strong convexity, and we can use it to change the update to incorporate it. And if we can take the, let's say, AGD plus and ACSA update and actually incorporate strong convexity. And for those methods, we are going to be able to show acceleration. There's also more black box reduction way of doing things via restarts. And I'm happy to tell you more about that offline as well.
Any more questions? All right, in that case, let's thank Alina again. So that's it for first.